The next formula that we're going to look at is this one here. And this is given on all the exams, year 12 in Australia, New Zealand, the UK, and the United States. What does this mean? Well, this one here, if you have a look at it, it means the change of reaction of the enthalpy. Now we're going to get to this in a second because this is a curly one. But notice we've got sigma, which means sum of, in other words, all added up. The bond energy is broken minus the sum of all the bond energies formed. Okay, so it's all of the bonds broken minus all of the bonds formed. So what does that actually mean? Let's say that we have a giant water molecule. So we have our oxygen here and our two hydrogens there. And we wanted to, let's actually connect those up. So we didn't have to actually, because that's an O. Just say that we wanted to break this up like Thanos in the Marvel movies into an oxygen atom and two hydrogen atoms. What would we need to do? We would need to get energy and put it into that bond so that the bond is so great that it breaks the bond. It's no longer necessary for that hydrogen to be bonded to that oxygen. And the same if we want to break up that one, we would put energy into that bond to break it up. And that energy is going to be in the form of heat. So we get to our problem of enthalpy. What is enthalpy? And it's a bit like entropy. If you ask 10 people, you get 10 different answers. But I want you to think of enthalpy, and I can barely spell it, to be honest. Think of it as the total energy of a system which is holding it together or breaking it apart. So back to our example here of the water molecule, we had to put energy into this bond and into this bond here to break it. This is enthalpy. We have increased the enthalpy of this molecule so that now these three bodies that come flying off with the oxygen and the two hydrogen now have more energy than they had when they were joined together. And that is what's meant by change in enthalpy. It's really the change in heat energy inside the system. So, with that said, so what is the unit for enthalpy? Well, enthalpy, technically it's an energy, so really so what's the unit for enthalpy? Enthalpy is a measure of energy. So if you said a joule, you'd be correct. But in this case, we're going to use a slightly different unit. And the enthalpy change is going to be measured in kilojoules. That's 1,000 joules per mole. Okay, so 1,000 joules per mole of a substance that we're breaking up. So it's the energy, one kilojoule per mole if we had 1 mole of a substance and we wanted to be like Thanos and disintegrate it into its individual parts, it would be 1 kilojoule per mole. So it's a bit of a tricky assignment to sort of wrap your head around that, but it's energy per amount of stuff. Remember, a mole is, what is it, 6.022 times 10 to the 23 number of atoms or molecules. So a lot. So it's not in grams. Be careful if they give it to you in grams in the exam, you need to convert it to moles. Got to be in moles. Everything must be in moles. So you might be asking yourself, okay, so how do we measure this? Oddly, we're not really worried about how much enthalpy is in a molecule or an atom or a system. We're only interested in how much it changes. We can't really measure how much is in there, but we sure can measure how much it changes. And we do that pretty simply just by measuring the temperature change. So the convention is this. If the enthalpy is greater than 0, i.e. it's a positive number, it means that the energy that we put in is greater than we take out. So the energy has to go somewhere, so it goes into the molecules and becomes the enthalpy of that molecule. So think of our system. If we have like a magic box here, and we want to break them apart, we put energy in, okay? That would be positive entropy. And the way to remember that is this is endothermic. In through the outdoor, you enter heat. Thermo means heat. Endo means in. Okay. If we have our enthalpy as a negative number, it means that when we do a reaction, here's our little reaction again. If we do a reaction, heat will leave that system into the surroundings. And just like in endo, out is exothermic. Literally means heat going out of the system. It doesn't disappear, it just leaves that system into the surroundings. Okay, very important to note that. Endothermic means heat goes in, exothermic means heat goes out. So how can we tell if something is endothermic or exothermic? Well, the way we would do it is we would have the experiment in a calorimeter. I can barely say it. And what it is, it's an experiment where we do the experiment in this little box and it's surrounded by water. And we can take the temperature of that water. We can put a little thermometer in there. Let's do the color actually. We have like a little thermometer in there. And if it's exothermic, heat will leave our experiment and go into the water, so the heat would go up. And if it's an endothermic reaction, it will take heat energy from the surroundings into the reaction and the temperature would go down. So this is literally what we do in a calorimeter. Oh, enthalpy calorimeter. Oh. Okay, so now we get a sort of a paradox. When we want to break bonds, is that going to be endothermic or exothermic? Maybe pause there, have a think about it. Usually when we break bonds, it's endothermic. Okay, so coming back to our water example, we needed to put energy into this molecule to break these bonds. And that energy can't just disappear. You can't make or destroy energy. You can only change its form. That's going to stay in that system, so the heat will increase when we break bonds. When we form bonds, this is probably, in fact, almost always, going to be exothermic. Heat will leave. So if we had our hydrogen And oxygen has enthalpy now, but by making these bonds, it needs less energy. So that excess energy has to go somewhere, so it has to leave that molecule. And the good thing for us is that essentially, as far as we're concerned, this number here and this number here are the same, but one is going to be positive and one is going to be negative. It's not quite that way in real life, but that's what we're going to presume in our little example. Okay, so let's explain what we mean by a state function. So a state function, you might think it's when we invite the king around and the prime minister opens parliament. It's not that kind of state function. What it is, it's a function which depends on the state, where something is. And I'm going to illustrate that by giving you an example of my favorite book, and this is Howard Anton's Calculus. So this is the example that I had when I was first year university student doing calculus, and if you look at the edition, you could probably guess how old I am. So let's say I take my edition of Howard Anton's Calculus, and I get in my car and I drive to the airport, and I get on a plane, and I get on a plane to Auckland. And then, of course, being Auckland, we have to change terminals, so I put it in the shopping trolley thing and I wheel it around their little magical mystery tour that they have in the Auckland airport, and I take a plane to Los Angeles. And then I take my Howard Anton's Calculus book and I walk across Death Valley to Las Vegas. And from there I take a flight to Paris, still with my calculus book. And then I figure, well, I'm pretty close to the UK. I'll go visit London. So I go to London with my calculus book. And then I take my calculus book to Sydney. And then I catch the plane home to Wellington. Now, if I take my calculus book and I put it in the same place as it was before, how far net has my book travelled? And the answer is not at all. It's still exactly on the same shelf. It's exactly where it was before I left. That is the concept of a state function. Irrelevant of how we get somewhere, it's where it is that matters. So here is my book, and I started in Wellington, and I went around here to Auckland, and then I forget where I went then, to Los Angeles, and then Las Vegas, and then where did I go? Paris, and then I went to London, and then I went to Sydney, and then I came back home. As far as the book is concerned, it went nowhere. Okay, if we start at a state 1, and after a process we're in state 2, this is state 2, state 1, as far as the only thing we're really interested in is what is this difference between 1 and 2. Maybe if I came home and I put my calculus book on the shelf above it, where I keep my fiction books, then I feel really bad because calculus isn't a fiction, it's non-fiction. But if I did that, how much had it moved? Well, probably about 20-25 centimeters. Even though it's been around the world, the net change, everything that it went minus everything that it did to come back, cancels out. And this is a really, really simplified version of Hess's law, which is a really great law that we'll get on to, but it's Hess's law in disguise. And we're not going to do Hess cycles or any of the complex stuff that Hess can let us do. We're just going to use the formula given and just the formula given to solve these two problems. So this first example is from 2016. It's the NCEA exam, although there's lots and lots of similar ones that I've seen out there. So we're asked to calculate the enthalpy change the reaction of butane gas, so 4 carbons with a double bond, C4H8, and hydrogen gas H2, it's that one here, into butane gas, which is just a straight carbon single bond with hydrogen. How are we going to work that out? Well, let's use our formula here. We need to work out how many bonds would be broken minus how many bonds would be formed. So let's pretend that we are Thanos from the movie. I can't remember the name of the movie, and I don't know the name of the thing that he hit, but he hits that button and half the things in the universe sort of disintegrate into atoms. We're going to do that here. We're going to be complete psychopaths. We're going to completely destroy this mole of butane and this mole of hydrogen and make a new gas. Okay, what are the bonds that we've got? So straight off we see a carbon-carbon double bond. So let's call this bonds broken in this one. So how many of them are there? There's one carbon-carbon double bond. Now, be careful. Breaking a double bond is not the same as breaking two single bonds. Different energies. So if you see carbon-carbon or hydrogen-carbon or whatever, a double bond just treated differently to a single bond. How much energy would we need to break that up? Well, 614 kilojoules per mole. We're going to say that there's 1 mole. So this is going to be 1 times 614 kilojoules. Okay, there's that one done. There are 2 carbon-carbon single bonds. So 2, how much energy does that take? 346 a pop. 346 a pop. That's those 2 done, and the rest are going to be carbon hydrogen. So 1, 2, 3, 4, 5, 6, 7, 8 of those. Hydrogen carbon, so 8 times 414. Is that all of the bonds? Not quite, it's all the bonds in this molecule, but don't forget we have the hydrogen gas. And this one just has hydrogen-hydrogen bond, and it's just one of them. So 1 times hydrogen, single bond to hydrogen, it's the only bond it can make. So 1 times hydrogen-hydrogen is 436. And then when we add them all up together, we work out how much energy we would need to break these 2 molecules up into their atoms. So let's do that. We're bringing our old friend Mr. Casio. So we've got 1 times 614 plus, and I'm going to put them in brackets, 2 times 346 plus, and this is where it's going to get fun, 8 times 414 plus 1 times 436, and we get 5,054 kilojoules. So 5,054 kilojoules to break it up. Okay, now let's work out what it's going to take to break those, to reform those bonds. So that's broken, and these are the bonds formed. Okay, so there are 1, 2, 3 carbon-carbon singles. So 3 carbon-carbon, and that's going to be carbon-carbons are 346 a pop. Just mindful it's just a little bit off the edge of the page. That's better. Okay, and then we have these hydrogen carbons, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. Hydrogen carbon, and we go to our table. Carbon, hydrogen, hydrogen, carbon, 414. So 10 times 414. So when we add all of those up, grabbing our calculator again, 3 times 3, 4, 6 plus 10 times 414, probably do it in your head, 5,178. So it takes more energy to form this molecule than to break it. Okay, so is this endothermic, exothermic? Well, let's apply our equation here. The bond of the energy is broken is 5,054. So the total enthalpy change minus 5,178. And we're going to have a negative number. Okay, so 5054 minus 5178. We have a negative number of 124. Does that mean we've discovered anti-energy or dark energy or antimatter? No, it just means it's exothermic. So it's exothermic, meaning heat will leave this reaction. And it helps if it's on the page. It's an exothermic reaction. So we have our reaction here. We do the reaction and heat will leave that system. It's now in the molecules need less energy to stay together. That energy has to go somewhere, so it escapes in the form of heat. So that is exothermic. Okay, another one. This is from 2015, I think. That might be the other way around. But let's apply our rules. So we have ethene gas. So 2 carbons bonded with a double bond with hydrogen, and it's binding with bromine gas to make this. What would that be? It would be 1, 2 dibromo ethane, wouldn't it? Yeah. Be pretty nasty stuff. And in fact, I think they made a mistake here. That should be a liquid and at room temperature, but let's go with it. Let's not argue. So ethene gas is this thing here. Bromine gas is this thing here. We want to destroy it and then build it up again into this new molecule. So let's work out the bonds broken and the bonds formed. So the bonds broken, let's do the bromine first. Bromine, bromine, it's 1 times bromine, bromine. And that's 1 times bromine, bromine is 193. So not a lot of energy to break that up. And then there are 1, 2, 3, 4 hydrogen to carbon. So that's going to be 4 times carbon to hydrogen, 414. Again, the order doesn't matter. Hydrogen, carbon, carbon, hydrogen. It doesn't matter. That's that done, and the only other bond is this double bond here, carbon, carbon. Carbon, double bond with carbon. Again, that's not twice a carbon, carbon. It's a single double bond of carbon, and it's 1 times 614. And we grab our calculator. Mr. Casio comes onto screen. 193 plus 4 times 414. I know you don't need to put the brackets, but put it in there just to show you. So 2,463 kilojoules. So to break up these two molecules, we would need 2,463 kilojoules per mole. I would have thought a bit more, but okay. Now to form this 1,2-dibromoethane, let's do that again. So how many hydrogen carbons? 1, 2, 3, 4 of those. 4 times hydrogen carbon. So that's 4 times hydrogen carbon is 414. There is 1 carbon-carbon single. So 1 times 346 Are there any others? No, just carbon bromo. So there are 2 carbon bromo. Someone's just dropped off a chocolate bar for me, so yeah. And they are 285. Okay. Each. So let's grab our calculator. Let's get this out of the way so I can hit my crunchy bar. So 4 times 414 plus 346 plus 2 times 285, and we get 2,572. Okay, is this going to be endothermic or exothermic? Well, remember, there's going to be bonds broken minus the sum of bonds formed. So this is going to be bonds broken is 2463 kilojoules minus 2,572 kilojoules, which nets as a number. Funny that. 2463 minus 2572. So we lose 109 kilojoules. We don't lose it, but 109 kilojoules leaves the system. It's a negative number, so therefore it is exothermic. And that means I can have my crunchy bar.